Hey, okay, so lesson 4.5 is about linear approximation. We've done a little bit of this already where we use the derivative as our new slope. And then we did y minus y1. So this is like y1. Here, I can write that. So this is the same as saying y minus y1 equals m, which is going to be our derivative, and then x minus x1. But notice how everything's just kind of changed the function notation a little bit there. And don't let that throw you off. It's still the same kind of thing. And then, so what's happened is, um, as we travel through this thing, they're using f of a and f of x, okay, and then and a is a moment where you can actually find the derivative, and then we'll travel along the function, whatever x happens to be. All right. So this is kind of what it's saying down here. So we've got a point x equals a, and then so this is the y1. This is our slope, and then x minus x1. All right. And then as you're going here, you can say, well, your function value, all right, could be approximated using a line. That's why they're using L of x. And then again, the same thing we already talked about. But this is kind of cool because the change in the function then could approximately be evaluated by the change in x times the slope. All right, I'm going to show that from a graphical standpoint in a second, so you can see exactly what that's talking about. And then the change in the function is just the two y values subtracted. So this would be like this would be like the change is going to be y2 minus y1. All right. And so why do we want that? Well, because then we can find an error by finding what was the actual change in the function and what was the approximated change in the function. And then you do, if you do a percent error, it's always the change over what the original was. So the original will be considered our exact, and then times 100, of course, will give you the percentage. All right, we'll work on that. All right, now, but graphically, this is kind of cool because, like, if this is a set time and space, a particular point where you're finding the slope, right? Then you travel along that line. Well, you have an error here. All right, so the error we will calculate. All right, so the error is going to be this e of x. All right. Now, this was f of a, and so if I travel straight across here, so is this particular y value. So this added y value here, as we traveled along the line, was calculated by the slope of the line times the difference in the x's. That's what you do when you are traveling. It's just that typically you would just travel one. So if I was doing a slope, I'd say, all right, like slope was a half. Then you go up one over two. You could think of that as traveling, let me say two. So up two over one, up two over one. So that's what I did twice. So I would do the slope twice, and that means I went up actually four. So I did that a couple of times, right? So I don't know what the unit value here is, but you do the slope that many times, and that many times is determined by the difference in your x's. Okay, we'll talk about it. Okay, so then um, again, this is talked about here. Now, whether or not that tangent line is an overestimation or underestimation depends on the curvature, which is really more unit 5, but we're going to talk about a little bit here. So if I have a tangent line that's under it, then that's going to be an underestimate, and that's because this thing was curving up, concave up. All right. And then if our tangent line is drawn on top of the curve because it was downward curving or concave down, it's an overestimation. All right, and we'll talk a little bit about that, but we're going to be doing that kind of thing with the concave up and concave down a whole lot more in the next unit. All right, so then actually finding the error, this is kind of cool because, like, say you found the difference in the two values, the real value, the exact value, and the approximate value. You found that to be 0.000. You had 3 zeros here. Well, then you could state that your error was less than this because the amount that we're off is 10 to the negative 4. That's in the realm of 10 to the negative 4. 1, 2, 3, 4, right? So you could say that your error is less than that because 10 to the negative 4 is a very, very small amount, right? And so we're within 10 to the negative 3 of this because that's the number of zeros we have, all right? I like that explanation a lot. The number of zeros you could put right there. Okay. All right. Cool. Okay. So let's do. So that takes care of that. And example one, there wasn't really a whole lot to write. So I'll just move on to example two right now. Example two is what you've done before. Okay, but they're wanting you to use this f of x notation instead. All right. So whereas we did y minus y1 equals m times x minus x1, and we did that. We've done that a lot. Okay, they're going to say that your x1 is going to be f of a. All right, so what they're going to say instead then is f of x can be approximated using f of a all right, and then the slope at that moment all right, and then x minus a. All right. It's the same thing we've been doing. And so then all right, and so in this case then the equation of the tangent line which let's see, what did they call that earlier? I want to call it the same thing. L. Okay. So the equation of this tangent line, we'll call it L of x. Okay. Is equal to, and that's going to be approximation for the function itself. So L of x would equal, I'm going to add this f of a. So f of a, so we're wanting to use 3, 3 negative 2. All right. So I would have had y minus y1. So that would be f of a added. So it's going to be negative 2. Okay. Plus our slope, which is 5. Right. And then x minus x1. And x1 is 3. All right, nothing new here. All right, you've done this before. All right, and so then it says use that equation to find the value of an approximate value of f of 3.1. So I could say this. So f of 3.1 could be approximated using L of 3.1. And so that's going to be negative 2 plus 5 times 3.1 minus 3. Again, nothing new. We've done that before. It's just we're using a little bit different notation here for it, but you can still think of it just like as before. So it's going to be negative 2 plus 5 times 0.1, which is negative 2 plus a half. And that's negative 1.5. Okay, so pretty soon we'll be talking about, all right, well, how good a job did that do? What's the percentage of error and that kind of stuff? That's coming. All right, so just kind of a little warm up there as the stuff that we've done before.